Hey everyone, and welcome to our journey into one of the most exciting fields of our time, machine learning. In this video, we'll explore how machine learning works, why it matters, and where it is taking us. Have you ever wondered how Netflix knows what you will love next? That's the magic of algorithms, learning from your choice. And how does your phone recognize your face? It's machine learning at work, turning patterns into predictions. We are diving into chapter 1 of hands on machine learning with Scikit-Learn, Keras, and TensorFlow. Whether you are curious about AI, aiming for career in data science, or just want to learn these buzzwords, you are in the right place. We will start with absolute basics, explore why ML is everywhere, look at its different flavors, and even cover some common pitfalls you will encounter. By the end, you will have solid foundation to build upon. So, what exactly is machine learning? At its core, it's about teaching computers to learn from data without being explicitly programmed. Think about it like instead of writing rigid rules for every scenario, we feed the machine examples and it figures out the rules itself. Pretty cool, right? So, why are so many industries turning to machine learning? The answer lies in three big advantages. First, many problems today are too complex for traditional programming, where writing a fixed set of rules isn't scalable. Second, machine learning systems can adapt to new data automatically without needing to reprogram. And third, ML helps us extract insights from massive amounts of data, patterns we might miss on our own also. Let's look at how machine learning compares to our traditional rule-based programming. In rule-based programming, you tell the computer exactly what you need with like a if-else conditions. It works, but only for a predictable tasks. Whereas machine learning, on the other hand, learns patterns from data. Instead of coding rules by hand, we feed the system examples, and it automatically figures out the logic by itself. This change makes ML powerful for solving real world problems. For instance, take example of image recognition. A machine learning model can distinguish a dog from a cat, not because we wrote the rules about cat and dogs, but because it learned from thousands of labeled examples or photos. Or consider another use case for spam detection, where ML systems have analyzed millions of emails to decide what is a spam and what is a non-spam email. And then there is recommendation systems like Netflix or Amazon constantly, which are learning your choices to suggest what you will most likely enjoy next. These are just few examples of what ML can do, and we are only scratching the surface. Let's start with supervised learning. Imagine you are trying to teach someone the difference between apples and oranges. You show them a bunch of pictures, each one labeled either as apple or orange. This is exactly how supervised learning works. You feed the algorithm data that already has correct answers or labels. It learns the patterns, and then it is understanding, okay, maybe apple tend to be red and round while oranges are like more orange in color and slightly rough. Once trained, it can then look at a new fruit or new example and identify if that is a apple or not. This is this is actually great for problems like spam detection, where we know which emails are spam and which aren't, or house price prediction, where we use past sales to predict the new ones. Now let's look at what would happen if there are no labels, like you just have a bunch of data and machine has to make sense of it on its own. That is unsupervised learning. Think of a child sorting a box of random toys. They may not know what each toy is called, but they notice the shape of these toys. Like there, some are round, some are square, some are triangles, and they naturally start grouping them. This is what happens here. Machine finds patterns and structures hidden in the data. This is ideally used for customer segmentation, where you need to group customers with similar behavior, or you can also use them in anomaly detection, like spotting fraud that doesn't follow known patterns. To sum it up, supervised is the algorithm where it learns with guidance. You have input data plus the right answer. In unsupervised learning, there are no answers, just data. The algorithm finds its own structure. You can think of it like this. Supervised learning is like a student with a teacher and an answer key, whereas unsupervised learning is like an explorer trying to figure out things without a map. Then, beyond supervised and unsupervised learning, there is a third major paradigm, which is reinforcement learning. This is completely different approach. Imagine like a character in a video game or a robot arm. The system, which we call an agent. This agent learns by performing actions in an environment and receive awards or punishments in return. So basically, depending on how it performs action, it is given a reward or a punishment. What is the agent's goal? Agent's goal is to learn the best strategy or policy to maximize the total rewards over time. So its main goal is basically try to make best moves and try to gain as many rewards as possible over time. Think of it like you teaching a dog to sit. You give it a treat, a reward when it performs the action correctly. This is the type of learning behind many amazing applications, from like there from beating the world champion in game of Go to controlling robots, and like Tesla, which is like even training self-driving cars. Now, let's look at batch learning, one of the most common approaches to training machine learning models. In batch learning, we take a large batch of historical data, represented here by this documents, and these are fed into a training process. This process builds a model which captures the pattern in the data. Once trained, the model is deployed and used to make predictions. A good analogy is like a student is studying for a big exam. You prepare for all the material upfront. You have all your books, you are learning them, and you are understanding everything and storing it in your brain in a way. And then you go write and test. There's no learning happening during the test. Just like the model doesn't train during the prediction time. But here's the catch. If you want the model to adapt to new data, you need to retrain it from the scratch. So this is basically a repeating process with the updated data set. Batch learning is great when your data doesn't change often, or you can afford to retain periodically. However, it can be resource intensive and also sometimes slow to react to recent changes. Then there is this another option of unlike batch learning, where the model is trained once on all available data. Online learning is like a dynamic approach. Here, data arrives continuously, either one point or mini batch at a time, and the model update itself incrementally. Think of it like learning a new skill every day, small steps that you build up to become master. This makes it ideal for situations with constant data flow, like stock prices or user behavior on website. It is fast, It is also adaptive and it works well when resources are limited or data keeps evolving. Now, instance-based learning. Instance-based learning is like learning by comparison. Imagine you are trying to identify a fruit you have never seen before. You look at it, then recall similar fruits you have seen in the past. Maybe it looks like an apple, but maybe it has color of a plum. Instead of building a generalized model, instant instance-based learning algorithms memorize examples. So when a new input arrives, so what the system does is system compares it with the stored data. Like it is actually looking at its neighbors and tries to make decision based on the closest matches. This is basically essence of what k nearest neighbor or knn algorithm does. It is simple, intuitive and effective when you have examples which are clean and well labeled. Now then there is another type of learning which is model based learning. What it does is it is all about building a generalized model from training data. Instead of memorizing, what it does is it tries to find underlying patterns and relationships to create a mathematical model that describes the data. Once the model is built, you can discard the original training data and use the model to make prediction. This is like finding the formula for this line that best fits a set of points. Most common ML algorithms like linear regression or neural networks fall into this kind of category. Now let's look at main challenges of machine learning. Imagine you're trying to learn about entire animal kingdom, but the only creature you have studied is a house cat. You'd miss out on elephants, birds, or everything which is in between. That's exactly what happens when our training data is too small or doesn't represent the real world. If your data set contains only one type of example and your model learns a narrow and a biased view of reality, what happens to the result? The model performs well on the data it knows, but it actually struggles or completely fails when it faces something new or when it finds data that is completely apart from what it has learned. So basically the key takeaway from this is we need enough data and it must also reflect reality. Otherwise all it does is garbage in and garbage out. Let's move to second major challenge, which is poor quality data. Even if we have enough data, if the data is noisy, incomplete, or filled with errors, the model's performance can suffer drastically. Take this example. We have a data set with obvious, let's say outliers, some missing values, or let's say few points that just don't make sense. If we train a model on this as is, it might learn the wrong patterns or also get confused altogether. That is why data cleaning is crucial. We need to identify and handle outliers or maybe impute or remove missing values and reduce noise. It is bit like trying to understand a message which is written in tone handwriting. Maybe until you clean it up you can't read it clearly. Remember, garbage in, garbage out. It's just as saying in it's a fact in machine learning. So before diving into fancy models, make sure your data is clean, consistent and complete. Now let's talk about challenge 3, which is irrelevant features. Imagine you're building a model to predict house prices. You have got features like size, number of bedrooms, and bathrooms, all good. But then somehow you also include the eye color of the homeowner. Sounds strange, right? That's a irrelevant feature. It adds no value and only introduces noise. Too many such features can confuse your model, which will definitely lead to poor performance. That's where feature engineering will come in. Instead of feeding the model raw inputs, we create some meaningful features. For example, we could create a new column average, average room size by dividing the total size by number of rooms. This gives us a mod. This gives the model a better sense of how space is distributed. So the major takeaway here is more features don't always mean better results. It's always about right features and engineering them thoughtfully. Let's talk about overfitting, one of the most common challenges in machine learning. Overfitting happens when a model learns not just the underlying patterns in the data, but it is also learning the noise. It tries too hard to perfectly fit every training point. Like you see here in this wiggly complex curve that it is basically trying to touch each dot. This might seem good at first. The model performs extremely well on training data, but the real test comes when new unseen data comes. As you can see, when we give it slightly different data points, the model complexity fails to generalize. Why? Because it hasn't actually learned the core pattern. It just memorized the training set. It is like a student who memorizes answers without understanding the concept. It is good during practice, but it actually struggles in the real exam. To avoid overfitting, we can add more training data. We can try to simplify the model, or maybe use regularization techniques to penalize complexity. In short, don't just memorize and try to understand. If overfitting is like memorizing too much, underfitting is opposite problem. Underfitting happens when model is too simple to capture the actual patterns in the data. In this example, the model is just a straight line, but the real relationship is clearly more complex. The real result, it measures the trend entirely. A model like this will definitely perform poorly on training data and also on the new data. It is not even learning enough to do well when it is trained. It's like a student who barely studies. They can't answer the easy questions, neither the hard ones. To fix uh, underfitting, we can use more complex model, maybe add better, more intuitive features, or maybe reduce overly strict constraints that limit your learning. Now, when we build machine learning models, we can't just throw all the data at it and hope for the best. That's like studying the exam answer key before the test. First, what we do is we split our data into three sets: a training set to teach the model, a validation set to fine tune and choose the best parameters, and then finally a test set. The test set is special, it always stays completely untouched until the very end. This way, it acts like a new unseen data which gives us a true picture of real world performance. Think of your machine learning model like a high performance car, the hyperparameters. They are just knobs, dials, and sliders that control how it runs. Unlike parameters, which your model learns from data, hyperparameters are set by you. They are decisions which are made before the training even starts. Tuning these settings, like learning rate, tree depth, or number of layers, can mean the difference between a underfitting model and the one that performs at its peak. Get them right, and your model goes from good to great. Phew. We have covered a lot of ground today. We have looked at what machine learning is, we have explored why it is powerful, we have also learned about different types of ML systems from supervised to unsupervised. batch to online, and instance based to model based. And critically, we have covered common challenges like insufficient data, overfitting, underfitting, and also importance of proper testing. Remember, understanding these foundational concepts, it's like building a strong house foundation. It makes everything you build on top of it much more stable and reliable. Don't worry if some concepts feel like a bit abstract right now. The more you dive into practical examples, the clearer they'll become. If you found this video helpful, make sure to give it a thumbs up. It really helps the channel grow. And if you want to continue leveling up your data science and machine learning skills, make sure to subscribe so you don't miss our future videos. We'll be diving deeper into practical applications and code in upcoming chapters. What's one machine learning application that truly fascinates you? Let us know in the comments below. We love hearing from you. And if you're ready to dive even deeper, I highly recommend picking up a copy of Hands of Machine Learning with Scikit-Learn, Keras, and TensorFlow. The links in the description. Thank you so much.